Hello, welcome back. This is a tutorial for our PL map code. It is composed of 3 Python files. One covers the light field module. In other words, there's light field functions such as uh, acquiring and then setting that acquisition file's name right here. There's like a whole timestamp, and it like takes the exposure time and center wavelength and put it into the name of the file and then saves it. And there's even a system where you can let like events occur and then it waits for an event. In other words, you can make you can synchronize things by calling is it set or wait. Um, in other words, we can implement this light field function into the motion of our script. Where's the script? Oh, yes. So this is the script. Um, this is the more important part. This is the most fundamental part of this tutorial. So what does the script do? Well, we need to specify the PL map's height and width, and then it has incremental steps. So you can specify these, and then it calculates how to move. Um, I set the map from bottom left to top right, only because it's an arbitrary reason. Actually, it doesn't really need to be from there. Um, Depending on which direction to go, the step size of the raster scan changes, but overall the commands are going to be largely the same. Just change the sign. These ensure that this starts from the bottom left, goes to the right, and it goes up, and goes to the left, and it keeps repeating that until it reaches a certain height. Yes, the certain height. Vertical scan and horizontal scan. Okay, and then we'll get to see this running or not actually. Uh, right now the program works, but we have reached this thing called the software limit. Now this thing is very important. It changes every time. Every time you have to be at the lab. I'm currently not at the lab. I'm remotely connected to this computer. The Axis One motor has reached a limit in the software. It can probably move if you were there, but this is something that's really confusing and that I still have to work on. And I would like to work for you guys. So if you guys actually send a command to say, "Hey, please move it in this direction," it will not work. You can do it the other direction too, and it will not work. Oops. However, if we do 2 PR and move 1 micron there, it will work. The command was carried out successfully, and here we go. So we'll have a PL map that's let's see, where is it? Front panel, move. So this is the front panel. This is I think I explained. I hope I did. I can explain it again. So this is just a website that tells you what is displayed on the box. It shows the motor's positions and it shows whether it's on or not. I'm gonna kill them all right now. That home button, do not press that. I repeat, do not press home. Home, it's unless we set it to the correct position, which is I really cannot tell. Uh, it will move rapidly to that position. This motor's range is 25 millimeters. In other words, it is possible that it moves so much that it hits the side of the cryogenic refrigerator and something breaks. We do not want that happening. In the case that we accidentally press it, we can always press space, right? Yes, abort. What that does is it turns it off, and then it turns what off? So it says off. I just defined that as send the command turn off motors for both axes, and and there we go. Okay, so certain functions. I think the other thing that's important about the script in regards to the synchronization with light field is that somehow we will have to implement a system where um, we will have the light field acquisition events integrated into the steps. So every step made, we will put like say, we'll call a acquire function. This is just acquiring per position, so per center wavelength, and then what kind of exposure time. We can implement these kind of functions into here, and then we could have a PL scan, wait for the file, wait for the change in center wavelength, changing the gratings, and then take a picture. And then once that PL stuff is done, it moves. So that is accomplished uh, by saying wait to the motors. Right now, we don't have that implemented, but it's rather simple. It's probably going to be implemented within Python uh, because this wait stop is the ESP specific function to stop all other action until this axis is done moving to its intended position. We can have more robust stopping mechanisms or synchronization mechanisms. We can discuss that later. Now, I am first going to invoke uh, this as just a demonstration for that. In fact, this axis does move. So, if you're interested in this, this just means that the Python keyboard function actually prints out what key you just pressed. Actually, sorry, here. Every time you press a key. And it's really annoying. It's going to bloat this terminal, so I set it to false. Let's first connect to the ESP. I pressed tab. This is the connect tab, the function, and now it's connected. It doesn't show it on here, but it is in fact connected, and I can prove it to you by doing a keyboard mode. So keyboard mode is just a mode I put for the convenience for Kamiar if he ever needs to do a PL scan manually. So this tells you the position. This is the current position. Axis 1 does not work right now, but axis 2 does. So let's see if it moves. Or first of all, let's make sure that the increments are not like 1 millimeter or something. Let's set it to 1 micrometer. So for now, we're only just bothering ourselves with axis 2. So let's put in 1 micrometer. And now it's the axis steps are set to our desired motion. Now let's move around. So as you can see, I pressed down and this number went up, and in fact it goes down, and here it also changed. I can demonstrate it again. So as you can see, it can go up or down. It is a little confusing because of the numbers, but if you were actually present and looking at the screen, you'll see that the motors are moving. All right, now let's go to the most important part, which is script mode. Let's change modes. So script mode, let's go to number 1. So we're setting up a PL map. So let's specify the map height. Let's have a 1 micron by 1 micron map, and let's set the horizontal step size to be 1 micron. It doesn't matter. It's not going to work. But the vertical step size is the most important part, and I will set this to 100 nanometers. All right, now it's going to start running. Oops, I'm sorry. That's my bad. I'll do it again. That was a mistake. I have to do it by I have to do a square. Now that's actually really important. We have to have a square map only because of the way I wrote it. The way it calculates the step size is it divides the map height by the step size, and that's the number of times it moves. So that's why we need a 100 by we need a square and even spacing map. So now this is moving. I also have for our convenience, I set up a relative coordinate for the map. These are in increments of millimeters. So the step size is 100 nanometers, and here you can see that the position is changing. The horizontal is changing more, and there's a reason for that. So we're going from bottom left to top right. We are seeing an oscillation because it's precisely this kind of motion where the horizontal axis is going from the positive direction into the negative direction and vice versa. And every time we should be seeing a change in real life, but because of the software error, right now we do not see any changes vertically. And then once the PL map is complete, well, on the motor side is complete. Now the challenge is to implement this file PL acquisition into each step. Now, something that I have to mention before I end this video is that the maximum speed, this doesn't matter too much. It does matter for the fact that I believe if you want the minimum incremental motion, we'll have to come up with a good speed for the motors. Remember, even though it says 50 nanometers as the minimum incremental motion, there are like we have all this load on this actuator. We cannot guarantee the accuracy of that motion. In fact, 1.2 micron is the typical accuracy that's listed for the current LTA motor. However, that is far larger, like around 20 times I think larger than the minimum incremental motion, which is 50 nanometers. So we are pushing it a little bit. This code works for ESP, but I demonstrated a 100 nanometer increments precisely because of this reason. Other than that, let's talk a little bit about light field. So light field, I will actually show you the initialization file. It is commented out right now because it fails to run one portion, and it's hard to, I think it has to do with the fact that it's a demo. So I'll actually run it. So it's creating it actually creates light field for you, so that works. And then right now it's demo Pixis. I could change it to another demo. Oh, there is no other demo. Okay, well, you can set the light field experiment to whatever experiment that you just saw. Loading an experiment is this step right here. So demo Pixis, you type in demo Pixis 2. You know, if you type it, it'll put it in for you, but if you don't type anything, it'll just load the default that's specified on our Python program. So it's loading demo Pixis again. So you can choose the gradings, exposure time, center wavelength, and file template. How does this all work? Well, generally, we check this thing called the lightfield.chm file. Right here, I actually have it in here. So if you look at this, if you go to the namespace, this is basically a gigantic namespace and a bunch of classes. So, for example, if you want to set the exposure time, then you want to go to the shutter, camera settings, Um, let's see. Oh, here we go. Shutter timing reading. Exposure time. Yes, and so and then it takes a double value, and you can actually set it in Python. Uh, this is exactly what is going on. You can put in numbers such as 500 nanometers, 1200 millimeters, and the type of rating, type of turret. And Python will actually light field here actually encounters a problem. I'm not sure if it's because this is a demo or if there's something more in play. I don't know yet. I will contact Sabir Layakat, who is who's in charge of the program, the software and program Python implementation for Lightfield. Um, the for now it doesn't work. I would love to try for our actual equipment and see if we can move on. Now, assuming that it did work, the next thing you do is to specify all the kinds of exposure times and center wavelengths that you want to try. We don't really have to use this. In fact, you could just manually set all the light field settings once we open light field. And then we can run things and say, this is different. This is just the file names. The more we're talking about, what are we talking about? Oh yeah, so the acquisition. So you can have things such as setting a value for the experiment, such as shutter time, center wavelength, rating, whatnot, and with the values. Usually, you can tell what kind of data type the value requires by looking at this experiment settings. Now, for this acquisition, usually the simple acquisition is you set the acquisition exposure time and the center wavelength, and then you acquire with a specified file name. Now, the acquisition is actually done by this acquire function, but the more important factor is how do you prevent like a rapid acquisition or like how does the program know, the Python program, how does it know that it's doing something right now and when is it completed? Well, that's controlled by this um, wait one and where's the set. So there we go. That's the end of this tutorial. Thank you very much. Bye.